Bienvenue à vous toutes et à vous tous. C'est vraiment un plaisir d'accueillir le professeur Emmanuel Passeguet comme professeur invité au Collège de France. Je ne vais pas la présenter longuement, puisque mon collègue Hugues Deté l'a fait vendredi passé. C'est sa deuxième leçon. Je vous rappelle simplement que Madame Passeguet est directeur du Columbia Stem Cell Initiative, qui est en fait un groupement de laboratoires à l'Université Columbia, qui est vraiment dedicated to the study of hematopoietic stem cells. C'est vraiment une concentration de laboratoires qui vise à un même intérêt. Aujourd'hui, Emmanuel va nous parler du Environmental Crosstalk and Bone Marrow Niche Regulation, et j'en profite en fait pour vous dire que son prochain cours sera demain, déjà, le 13, et qui parlera des myeloid cell population, adaptive and maladaptive myeloid cell population production. Emmanuel.
Merci Denis. Et je veux juste changer une chose, qui est que le Columbia Stem Cell Initiative est dedicated to the study of broadly stem cell, not just hematopoietic stem cells. So we have skin, intestine, gut, and a lot of iPSC and disease modeling with human derivative. So thanks for being here, and I can take question in French or comment in French, but I will still give the lecture in English. And the second one is a follow-up on the first lecture on the principle of hematopoietic stem cell, now talking about where do these stem cells reside and how this niche environment controls that function. So just a little recap of the first lecture. The blood system, highly hierarchical, starting with the hematopoietic stem cell at the top of the hierarchy, multipotent progenitor, which decide fate decision, commitment to the myeloid lineage, commitment to the lymphoid lineage, a lot of committed progenitor, an alphabet soup of letter to indicate these different population, in particular granulocyte macrophage progenitor here controlling myeloid cell. What you see in the movie is on the stroma layer modeling the bone marrow niche microenvironment. One hematopoietic stem cell let go for 7 days, and that's acceleration of cell cycle when the stem cell leave quiescence and commitment to differentiation with this lot of different change in cellular activity, migration in the niche, as well as commitment to differentiation. And of course, the transition to a world of single cell analysis, which affect as well now the study of the niche. So where is the niche? Well, within the bone marrow cavity, meaning within a shell of bone, which is the toughest structure in the human body, very stiff, very strong. And inside this shell of bone, you have the marrow content, where you have a lot of vasculature, and this is mostly representing the blood vessel, but it's highly, highly packed with cell. And in fact, when you do atomic force microscopy and measure the stiffness, you have a very close to the bone, to like basically 5 cell diameter, extremely stiff environment, a lot of extracellular matrix protein deposition, which made the environment very stiff. And within the marrow cavity, away from the bone shell, you have the most soft tissue in the entire body, even softer than the brain. So, and you have a very unique architecture of the vasculature, which is very few vessels enter, cross, breach the bone shell, enter the marrow cavity, and then you have this artery which go to the middle of the bone, together with a central vein. You have the central artery as well, which then sends this arteriole which go down towards the bone surface, and in this radial view, sagittal view, go away from the central marrow. Then you have this very dense like layer of artery along the bone surface, and then they transition to a sinusoidal network, which then go back to the central vein. So big difference between artery is that they are surrounded by smooth actin muscle, and that's where you have a lot of pulsation and like blood flow, versus sinusoid do not have smooth actin muscle surrounding them. They are really fenested. There is much less blood pressure, and that's basically where the cells are living, moving away from the bone marrow cavity. So very unique vasculature structure in the marrow. You have a lot of cell type, and this map of single cell analysis really shows the complexity and the diversity of the cell. The mesenchymal cell population, which came in many different flavors, and we'll go over that. Endothelial cell, arterial endothelial cell, sinusoidal endothelial cell, which I mentioned, neuronal termination, a lot of parasympathetic innervation in the marrow cavity. Then a lot of immune cell, all the mature blood cell, and a lot of these HSPCs, this stem and progenitor compartment. So when we talk about the bone marrow niche, we talk about an ecology of cell type. You have mesenchymal, endothelial, hematopoietic, adipocyte, fibroblast, a lot of different cell type. It's highly regionalized. I already mentioned the stiffness aspect along the bone surface, but there is very much a different environment close to the bone, the endosteal region, versus the central marrow. It's bathed by bone marrow fluid, which is which is a way to describe what you can basically squeeze out of the marrow when you cut open the end of the bone and flush out with a needle the little fluid which resides there. This is what we can harvest as bone marrow fluid, and in composition it's extremely different from blood serum. And there is a lot of secreted or bound factor which can be obtained in this bone marrow fluid, as well as metabolite, exosome, a lot of different stuff. So which again show very different composition and likely macro domain within the marrow cavity compared to blood serum. What match and migrate from the blood to the bone marrow fluid is a lot of inflammatory cytokine. When there is an inflammation in the distal tissue, increase in production of pro-inflammatory factor, this really is measured and felt and observed as well in the bone marrow cavity, in this bone marrow fluid. And there is a lot of other physical factors. I mentioned stiffness. There is as well hypoxia, extracellular matrix composition, which really introduce a great deal of diversity and complexity within the marrow. What I want to make sure people realize, because with this static image and cartoon of the system, we lose the concept that hematopoietic stem cell and progenitor and mature cell are extremely mobile, and they do not reside statically in one place in the marrow. They move around, and the best characterized one is the hematopoietic stem cell. I mentioned that a little bit in my presentation last week, but very essential fundamental property of HSC, in addition to self-renewal and differentiation, is really migration and mobilization. And parabiosis experiment, which are old-fashioned experiment where you surgically link together two mouse together by just cutting the skin and suturing it and letting the wound healing process progress normally. And roughly a week after the surgery, you now get a shared circulation between two mice. And this old technique has been used to show that when you can mark one of the mice with GFP and therefore trace their stem cell coming from this GFP positive mice into the non-GFP mice, that stem cell really go in and out of the bone on a very regular pace. You have constitutively inner mice around 100 HSC, which are in the circulation, with a residence time of 1 minute or less. So very transient presence in the blood. And then they go back into a bone, and it can be any bone in the body. So there is a lot of migration and change around where the niche, where they find their niche. And again, I mentioned last Friday this paper which shows that, like, when they are in the circulation, they as well enter tissue. And in this tissue, they can either sense local infection and differentiate as a first line of response, or if there is no signal for them to stay in this organ, enter the lymphatic system and be recirculated into the blood and then into the bone. So this approach of migrating stem cell and parabiosis experiment have allowed to disprove this concept, which was in the early 2000s, that there were transdifferentiation of many organs. You could take liver, you could take skin, you could take brain, and you can form blood cell out of this other differentiated tissue. In fact, is because the stem cells are circulating and can be found in this tissue. So, yeah, go ahead.
We should take question at the end because it's recorded.
Okay, I didn't know. Okay.
No problem. Keep this question in mind. So, which makes this identification of where are the hematopoietic stem cell niche and the microenvironment, the cell type, which are important for their regulation and function, much more difficult to address, because we are not looking at a static structure. We are looking at a very dynamic structure. And when you look at this regionalization and compartmentalization between the endosteum and the central marrow, we can see that the ratio of the various cell types is rather different. There is more stem cell in the central marrow than at the endosteum, close to the bone. Conversely, there is more lymphoid progenitor. This CLP stands for common lymphoid progenitor at the endosteum, close to the bone, than in the central marrow. And for each cell type, we see some bias toward localization. I already show the different, some aspect of the different structure between the endosteum, where you have osteoblast, here labeled with Col 2.3, which line the bone surface, and the arteriole as well, which line the bone surface, versus the central marrow with this very particular leptin receptor positive mesenchymal stroma cell population, which are marked here in this reporter mice with the red marker, as well as this very dense network of sinusoid. And stem cell can be found directly associated with mesenchymal stroma cell. This is an example of Paul Freinet lab showing this red stem cell close to the endosteum actually, but still in a perivascular localization associated with a nestin positive mesenchymal stroma cell. And in a more recent work from Dan Lucas' lab, which here the cells are shown by mask and ball. That's why it makes it more easy to see the red dot, because they are actually red ball instead of real cell. It's a modelization, but that's shown erythroid progenitor, which are basically assembled along the sinusoidal blood vessel in what we call production line, which is where erythroid progenitor differentiate, start producing progeny very close to the sinusoid, along the sinusoid bed, and therefore really capable to migrate very quickly into the circulation. So, but studying the niche is plagued with many different, a range of challenge. First of all, tissue digestion, which people with working on solid organ are confronted with, but now we are faced to that in the blood field. The blood has long been considered as a liquid organ, which I hate as a term, but it's true that you can get single cell by just flushing the marrow content, and you have to do nothing to get single cell. But when you start looking at the niche, that's a different ballpark. So you need to use dissociation, and that creates a bias in isolated cell. There is a lack of consistency in cell type identification, and here are three landmark profiling paper by single-cell RNA-seq, which are shown here like the correspondence between cell type and quantity of cell. And as you can see, is all over the map. There is absolutely no consistency in the labeling of the population. And there is very little attempt so far at reconciliating imaging, what we can observe when we look at the marrow, flow cytometry, which is a way to isolate said population based on surface marker, and those molecular data. So that's really what we, the challenge that we tackle in my lab in a recent year, which is to really try to develop this method of compartmentalized flow cytometry approach, where we take on one hand, so we first, flush the marrow plug. And it's very important to flush the marrow plug intact. If when you flush it, it fell apart, you will be losing a lot of this trauma population, especially endothelial cell that you are trying to harvest. And with a marrow plug, which is a stuffed marrow, very short digestion time to get this central marrow preparation. Then when you have flushed the marrow, you can take the bone chip and you can crush the bone. With mortar and pestle, digest them with collagenase, same enzyme than for the marrow plug, but you need much longer digestion to really separate the endosteal bone adhesion cell to get them free and to be able to analyze them by flow cytometry. So then you deplete all the hematopoietic cells, which are this PEN CD45 marker, as well as marker for red blood cell. And you can then run that in single cell analysis. And when you do that, red is endosteum, blue is central marrow. You can see that you get very different population, red and blue. Very little overlap in terms of the cell type. Then what second very striking observation is still the degree of hematopoietic cell contamination. So double negative gating, which is what this trauma gating here, this red and blue gating is, which is everything which is not marked by your positive marker, is a terrible way to sort cell. You get a lot of contaminated and you still get basically stem cell, also HSPC, a lot of erythroid cells, which are on their way to lose their nucleus and to shut down transcription, therefore cell surface expression, and a lot of neutrophil and lymphoid as well. So every atlasing published so far which show no hematopoietic contamination is because they have informatically excluded hematopoietic cell. But there is always a lot of contamination. But you get very clearly your mesenchymal cluster and your endothelial cluster. So we did here what I already showed you last time with the hematopoietic system, which is really trying to get a convergence between a way to isolate this cell population by flow cytometry and molecular identity. So on this endosteal population, we can apply this very standard collection of markers, which first identify endothelial cell and separate sinusoidal endothelial cell from arterially endothelial cell. In the endosteal population, it's mostly arterially. In the central marrow population, it's mostly sinusoid cell that you can get. And then from non-endothelial cell, you then can use this other marker, CD51 and SCA1, to identify osteoprogenitor in this SCA negative, as well as this K positive MSC, which are as well the nestin positive MSC described by Paul Freinet, which are basically this periarterially mesenchymal stroma cell. They are absent in the central marrow because there is very little arterially in the central marrow. In the central marrow, what you mostly have is this leptin receptor, PDGF receptor positive, leptin receptor positive mesenchymal stroma cell. There is a little bit of them at the endosteum, but not as much as in the central marrow. And in the endosteum, what you mostly have is this succession of progressively more differentiated multilineage mesenchymal progenitor and mesenchymal progenitor. So you have the dominant population and the minority population at both localizations that you can isolate. And when you look with this molecular profiling, you can see that, as expected, population in flow cytometry are not homogeneous. The MSCL actually contain 3 main molecular subsets, MSCL1, MSCL3. MSCL3 is very osteolineage committed. MSCL2 is very adipogenic committed, and it's really the endosteal population. So again, separation of function based on spatial localization. The MSCS cluster by flow cytometry is 2 populations, the true mesenchymal stromal cell, as well as a fibroblastic progenitor, indicated as FPR. And then in this multilineage mesenchymal progenitor, you have both the commitment to osteoprogenitor and the commitment to chondrocyte progenitor. We have now a marker, that's the beauty of doing this molecular analysis, which allow to separate these two activities, and we are continuing building this comparison between flow isolation and molecular understanding. And the Moore committee has 2 osteoprogenitor 2 and 3, and 1 more mature chondrocyte progenitor. For the endothelial cell, that's a very clear separation between the sinusoid and the arterially endothelial cell, and actually this narrow hourglass connection between 2 is basically arterially endothelial cells, a few one we can isolate in the central marrow compared to the one which are at the endosteum. So we can project all the molecular data from SMART-seq, which is more in-depth molecular analysis of sorted cell at the single cell level, or do the 10x analysis of this sorted population and project them on this map. So that's we are fairly confident in our labeling approach. We can reanalyze previous data set which have been published, the 3 atlas I show you in the previous slide. Again, a lot of hematopoietic contamination in this 2 first atlas. This one doesn't have hematopoietic contamination. It's I'm blanking on his name. Anyway, he worked with reporter line, so it's sorted reporter cells, so that's the way you don't get hematopoietic contamination. And very soon we will have our niche scribe, which is the same methodology of cell comparing cell identification and with flow cytometry and molecular data. So the most important point now is that we can use this approach, which is molecular identification of the cell associated with cell sorting of the population, knowing exactly what we are getting to find new information about the bone marrow niche and this environmental crosstalk with the hematopoietic system. So we started by first revalidating some of the knowledge about the whole system, which is sinusoid and arterially, different location. Indeed, molecular expression of gene are associated with gene identity corresponding to arteriolar endothelial cell with JAM2 and BCAM, or sinusoidal endothelial cell with TAP2 and FLT4. So, in terms of gene expression pathway, what do we see? We see very clearly that they have sinusoidal endothelial cell have higher VEGF receptor signaling, we can take VEGF receptor reporter line, VEGF receptor 3 in that case, use flow cytometry, look at sinusoidal endothelial cell, arterially endothelial cell, and indeed we can validate this higher VEGF signaling in this sinusoidal endothelial cell population. We see increased absorption, suggesting that sinusoidal endothelial cells are more permeable, and you can design experiment to test that, where we inject dragon bead, fluorescent bead into mice, and then measure the degree of absorption, so number of beads which are uptaken by sinusoidal endothelial cell or arterially endothelial cell. And by flow cytometry, we can see that sinusoidal cell is really where cell trafficking is happening. And we can see that sinusoidal endothelial cell express leukocyte adesin, which are very important for the rolling and adhesion and extravagation, which are very important for both stem cell and leukocyte and a lot of blood cell to migrate in and out of the bone marrow. So we can recapture the biology of the sinusoidal endothelial cell, which is very much the part where cell trafficking is happening in the marrow. For the arterially endothelial cell, similarly, we can show that they have the greater expression of tight junction component, indicating that nothing is getting through the arterially, is just flowing the blood into the marrow. And they have the greater notch activity in the whole system, which again is a well-known property of this type of endothelial cell. So for the mesenchymal compartment, it's a much more complicated question. There is a lot of controversy in the field, mostly associated with developmental angle. It's like, what is a skeletal stem cell? Which kind of mesenchymal stem cell is very important to build the bone and the development of the marrow cavity between late embryonic development. Fetal bone are formed around E18, it's mostly chondrocyte, there is no open cavity. When the mice are born, you start to see open cavity, you have a lot of different cell type. Macrophages are very important in shaping the opening of the cavity and really like the structure of the niche. You have the hematopoietic stem cell which start entering the marrow, this emerging marrow cavity around E18.5. 2 weeks after birth in mice, all the hematopoietic are in the marrow, they are still not quiescent, they need to transition to quiescence, meaning the stroma now is acquiring its adult property towards a month after birth. These data are less known in human in terms of the timing and the sequence of events, but there is a lot of controversy on what's the dominant mesenchymal stem cell population, what play a role in shaping the bone, giving chondrocyte, important for adipocyte and so forth. So what we did was to assemble 3 independent data sets, filter out hematopoietic cell and endothelial cell, and perform the CCCA integration. And that's the resulting UMAP coming out of this data, where you can see different expression, for example, for leptin receptor or for SCA1. And actually, when you do a lot of projection of differentiation, you can see that differentiation starts at these 2 nodes, the actual leptin receptor MSC and this SCA1 positive MSC. And from both, you have, from the leptin receptor, you have adipogenic differentiation and osteoblastic differentiation, and from the SCA1 MSC, fibroblastic, chondrocytic, and osteoblastic differentiation. And in fact, the gene identity of this leptin receptor MSC corresponds to what we identify as MSCL, and this SCA1 positive MSC to what we identify as this MSCS. So, in terms of their functionality, they are extremely different. There is a much greater osteogenic potential from the MSCL, which is highlighted by their molecular profile, but as well functionally when you sort the population and grow them in culture, you can see that there is a lot more alkaline phosphatase positive activity or Van Cosa staining, which mark bone formation from the MSCL. The little caveat here is that all this endosteal population, MSCS osteoprogenitor, that should be MPR, sorry, and this mesenchymal progenitor grow directly on plastic and form fibroblastic colony very effectively. The MSCL, which come from this soft marrow, do not grow on plastic. You can put it, it doesn't grow. You absolutely need to use hypoxic condition and IROC inhibitor to really block the sensing of the stiff plastic. Then you can get a fibroblastic colony that can be formed and used to differentiate along the bone lineage. And you can see here in this picture that actually the MSCL in the central marrow, which are those one as well, are much less effective at forming bone than the MSCL which are directly isolated from the endosteum. So again, a gradient of possibility associated with spatial localization. Conversely, the endosteal population, MSCS and their derivative, are much more effective at forming fibroblastic colony and have much higher chondrogenic potential. And in fact, their function in vivo is very most important in forming the chondrocyte early phase of development versus the central marrow and endosteal MSCL are very important in maintaining bone formation, even late during adulthood. So their localization as well is striking. In this image of a Walmond femur, you can see the central vein for reference is indicated here. These are arteriole, big one. These are small arteriole. These are large arteriole as well shown in the central marrow. But the green cell, which are shown by mask, and the same principle of putting a ball instead of just showing an actual cell. Also here you have the actual staining pattern in the image. The leptin receptor MSC are very much in the central marrow. This is very significant versus the MSCS are really along the arteriole and somewhat enriched at the endosteum, but mostly are an arteriole associated population. So what this told us is basically we revisited some known or refined some known feature of the niche with the vasculature and their role, and the mesenchymal stroma cell really showing that this subset of MSCL, especially the one located at the endosteum, are extremely important in bone maintenance, bone being the site where a lot of lymphoid progenitor reside and function, versus the stem cell and a lot of migratory cell type, especially along the myeloid lineage, are really tagging along and in close association to the sinusoidal endothelial cell. So, big question next is, how do this stromal spatial compartment regulate hematopoietic response to stimulation? That has always been a focus of my lab. How do you challenge the system, or the system respond? And I will just show you one example with viral infection, which is what we model with response to poly-IC. Poly-IC is read by TLR3 and use an immune response through MyD88 and then stimulate the production of type 1 interferons, which then act on target cell and really induce a strong inflammatory response. So what we see on the stroma when we give poly-IC to the mice is basically we start to see upregulation of SCA1 in this MSCL population. So SCA1 is one clear target of interferon. You have an interferon response, SCA1 goes up to the roof. In hematopoietic cell is a big problem to follow hematopoietic stem cell biology in following type 1 interferon is this upregulation of SCAR1 in a lot of progenitor population, which really confuse the analysis of the system. And in fact, this upregulation of SCAR1 is found on the stroma as well, but specifically on this MSCL. What we see is if you do a kinetic with repeat poly-IC injection every 2 days, is basically we completely lose the normal MSCL and it's replaced by this inflammatory MSCL. And it's a very quick response in basically after 1 injection. There is as well some change at the endosteum in all the endosteal population, but functionally we have not seen that much of a consequence on this cell in terms of their gene response. When we did single-cell RNA-seq after 2 injections of poly-IC, harvest the cell on day 3, you can see that the green cluster, which are all this MSCL cell, is completely gone and replaced by this inflammatory MSCL. So it's not just SCAR1. It's an entire inflammatory remodeling of this MSCL population, which is quantified here with the 10x stroma distribution at the central marrow as well as at the endosteum. We now get only one type of MSCL, this inflammatory MSCL. And it's because the MSCL compartment is the only one responding to interferon. We trace that with this MXC1 Cre Rosa MTMT mice, which is, it's start by being all red, tomato, and when you have in response to poly-IC is the way to induce this MX1 Cre reporter line. When you induce, when there is Cre activation, you transition to expression of the green fluorescence protein, GFP, and you can see that MSCL respond extremely acutely to an injection of poly-IC and a lot of green fluorescence versus MSCS have a limited response and none of their derivative actually transition to green expression, indicating that they are insensitive to interferon challenge. MSCL have much higher level at the gene expression level of a lot of these interferon transducer and response gene. So that's a SmartSeq data set on this population. So they as well have a signature of interferon activation, where we can see that the motifs which are the most enriched in the gene being expressed are all interferon associated, as well as expression of all these target gene. So, and more importantly, when we use a knockout mice, which is a pan knockout of the interferon receptor, and do the same challenge, poly-IC challenge, 2 injection, look after 3 days, basically we do not see this induction of this inflammatory MSCL population when there is no sensing of interferon. What happened to their biology? We have the gene expression of these cells. Basically, what we see is that they lose their ability to form fibroblastic colonies. So they lose their differentiation potential when they are challenged with interferon. They do not form colony, which are the fibroblastic colony, which are the prerequisite for bone formation. So we couldn't assess their ability to form bone because they do not form the initial step of this differentiation process, at least in vitro. But what we could do is really test their functionality in vivo with this model of bone drilling into reporter mice which are which express leptin receptor with a tomato reporter associated with COL2.3 and EGFP. So basically you have green osteoblasts, red MSCS, and when these MSCS are stimulated to form new bone, new osteoblast, that become yellow. because red and green equal yellow. So we use these mice for 13 days, we inject them with poly-IC, then we wait, and 14 days later, we inject them for 13 days, we drill the bone in the tibia, and we wait for 14 days to see the bone healing process and the genesis of new MSCL-derived osteoblasts. So in PBS control injected mice, you see a lot of this yellow new bone being formed at the drill side. You still see some yellow, but this is much more reduced. The size of the callus is much more reduced, and actually the mice never fully heal their bone within the time frame. We had let them, some of them go longer, and even after a month, we can still see that the bone is not fully healed. So this reprogramming of the MSCL fate induced by interferon signaling really block the ability to differentiate. What they do instead, they overexpress a lot of inflammatory chemokine. And these are shown here by the GO pathway analysis done on the single cell, but mostly in this graph showing expression of CCL5 and CXCL9, which are really boosted, so much more increase in this inflammatory MSCL, which cannot differentiate anymore, but become engine to produce inflammatory chemokine. So that was a good thing because it allowed us to test the effect of this inflammatory chemokine. So we first look in the bone marrow fluid of mice injected with poly-IC, same model, 3 days after, 3 days total, the next day after the last injection of poly-IC, and we could confirm in the bone marrow fluid much higher level of CXCL5 and CXCL9, and by cultivating inflammatory MSCL in a dish and measuring in the supernatant of this culture, we could as well see increased production of CCL5, really indicating that locally this inflammatory MSCL secrete a lot of this chemokine. What this chemokine do? They basically completely change monocyte trafficking in and out of the marrow. What we have is in poly-IC injected mice, much less of monocyte being present in the peripheral blood, versus in the bone marrow, we see now retention of monocyte in these poly-IC treated mice, which you can visualize as well by imaging on bone section with Ly6C monocytic marker staining. And you can see that everywhere now we see monocyte staying put in the marrow instead of being circulating out of the marrow. And this is very much a chemotaxic response, because we can model that in this transwell assay, where you have a micro well with pore at the bottom. On top well, in the top well, you put bone marrow cell, which in this case are isolated for interferon deficient mice in order to not have the cell sensing the remaining interferon that is likely present, still present in the bone marrow fluid of either PBS or poly-IC injected mice. And we measure the chemotaxis of this cell in the top well towards the factor being present in the bone marrow fluid. And we can see that monocytes very quickly migrate to the bottom well when they are exposed to poly-IC, the bone marrow fluid from poly-IC treated mice. And there is absolutely no effect on monocyte or in any other cell type. So it's a very monocytic specific response. We as well use genetic approach to inactivate interferon receptor solely in the leptin receptor subset of mesenchymal stroma cell. We see in that case a diminution in this inflammatory MSCL, which is quantified here, and a diminution in the retention of monocyte. It's not complete. If we use a pan knockout for interferon receptor, we see absolutely no retention of the monocyte in the marrow. We do not see actual induction of inflammatory MSCL. So that's really indicative that there is additional secretion by other cell types which contribute, but still a central role of this inflammatory MSCL. And in fact, the gene downregulation secretion of CLCX5, expression of CLCX5 or R7 is not completely abrogated in this MSCL-specific knockout compared to PEN knockout of interferon receptor. So the monocytes, which are retained in the bone marrow cavity, you see them increase in number in this whole bone marrow single-cell RNA-seq, increase in number compared to the PBS-treated mice. And when we look at what they are, we see every feature of monocytic activation. So increase class 1, MHC class 1 expression, cathepsin G. We validate on the surface of the bone marrow macrophage this increased expression of MSC class 1, ROS content, really indicating retention in the marrow of this hyperinflammatory monocyte. This response is transient. If we do only these 2 injections, 3 days of poly-IC, we have the peak induction of inflammatory MSCL, the peak production of CLCL5 in the bone marrow fluid, and the retention of monocyte. But if we let them wash away and wait over this 25-day kinetic, we basically see that it basically returns to steady state. So it's very much an acute response of the bone marrow niche microenvironment in response to an inflammatory signal, which translate the inflammation, the inflammation into local production of chemokine, cytokine, which really retain tissue-damaging monocyte in the bone marrow cavity and likely contribute to all the cellular impairment associated with viral infection and inflammation. And the diminished contribution to bone fracture repair as well indicates that it's not surprising of some event of bone fragility associated with long-term chronic inflammation and this kind of like inflammatory remodeling of the bone marrow niche. So altogether, what we detailed to you in this work, which has just been accepted for publication and should be in press relatively soon. An earlier version is available on bioRxiv, but it doesn't have all the work which we have done to satisfy the reviewer. But it provides really a simple and broadly applicable. So, and we want to make it the most accessible with easy to utilize, like the niche script program, that people can really apply it without resorting or needing to use fluorescence reporter mice to like map the change in the bone marrow niche microenvironment. So it's really a combination, bridging flow cytometry with single cell analysis. So we do provide some refined understanding of niche feature, known or controversial feature, but I think the key point, the key fundamental biologic point of this work is that it demonstrates that inflammation perturbs normal hematopoiesis by remodeling MSCL, a feature that we already found during aging. In 24-month-old mice, we have this increased inflammatory MSCL, and that's what put us on the track of looking at this population and its effect. So the malignant niche has been studied in detail by different groups, including ours, and there is a lot of remodeling of this various population in the niche. They are all fairly disease-specific modification. Again, it's hard to make generalization. Will it be an effect on the endothelial cell, the osteoblast? Work done long ago in my lab, we work on CML with BCR-ABL-driven chronic myelogenous leukemia. Actually, the remodeling is on osteoprogenitor, which lead to fibrosis at the endosteum. And that really creates a self-reinforcing niche for the leukemic initiating cell. Fibrosis in model of JAK2 malignancy or myelofibrotic model emerged from MSCL, not in the central marrow, not at the endosteum. So really very different mechanism. And for me, study of the niche is really the new frontier of what's really interesting in the hematopoietic field. There is a lot of work trying to map the same process in human, and a beautiful paper last year from UPenn has done a lot of this profiling that I show you in mice, done in human, combined with spatial transcriptomic, which was tour de force, because in our end, spatial transcriptomic on bone marrow in the mice doesn't work. There is a lot of background, especially this density of granulocyte and monocytes stacked up all the probe you throw at them, so it has been fairly challenging. But there is a new way of doing bone marrow niche imaging with reporter mice, labeling various cell population, or just multiplexing imaging, which now go up to 40 markers, which can be put together to really image feature spatial localization, crosstalk, and interaction. And that drives a lot of investigation, which remain open question in the field. How do stem cell number is controlled by the microenvironment? Where is the spatial localization of progenitor, especially when you challenge the system and mount an activation of like increasing blood cell production, and evaluating all this environmental crosstalk, cytokine contribution, exosome, microtunneling between stroma cell and hematopoietic cell, all of the things which are really used and hijacked by malignancy to really support the growth of malignant hematopoietic cell, as well as other cancer types, such as metastases, which lodge in the bone and are likely using the same kind of process to grow and prosper. So, with that, I want to stop. The person in my lab mostly implicated in this work is James and Ray. And I thank you for your attention. And I am more than happy to take questions in English or French.